Hello there, welcome back to my YouTube channel. So in today's video, we'll be looking at organic chemistry. Organic chemistry is a widely spread topic in chemistry. And what does that mean? Organic chemistry is just a study of compounds that contain carbon, and they are compounds that are found in living things, or they are compounds that are said to be made from living organisms. So any compound that contain carbon and that can be found in living organisms or made from living organisms, they are known as what? Organic compounds. And the study of this compound is what organic chemistry is all about. Example of such compounds include ethanol, include methane, include protein that are gotten from living organisms like plants. It also include carbohydrates, which is a major source of food nutrients for living organisms. It includes everything that you can find in a living organism in as much as that compound contain carbon. So quickly, we are going to be looking at some of the ways by which you can represent organic molecules. I mean, the formulas that are used to represent organic molecules. Basically, we have four formulas for representing organic molecules. The first formula that is commonly used to represent organic molecule is the empirical formula. The empirical formula shows the simplest ratio of the different types of atoms present in the molecule. An example of such formula is this: CH4. Another example is CH2. In these examples, we can see that in the first example here, we have just two atoms, and that is carbon and hydrogen. We have just two different atoms, carbon and hydrogen. Same thing with the second example too, we have carbon and hydrogen. But what is the difference? In the first example, the ratio of carbon to hydrogen is 1:4, while the ratio of carbon to hydrogen in the second example is 1:2. Now, looking at these examples here, we can see that this is the simplest ratio that we can ever have. The simplest ratio that you can have is 1:4 for this particular example here, which represents methane. Nothing can divide it further. The same thing with the second one, in which you have the ratio to be 1:2. And that is what empirical formula is all about. In my other videos, I explained how to calculate the empirical formula. So you can do well to watch that video to have a better understanding of how to calculate empirical formula. The second type of formula that is used to represent organic molecules is the molecular formula. Molecular formula shows the actual number of each type of atom in a molecule. Remember that empirical formula tells us the simplest ratio of the number of atoms in a molecule, whereas the molecular formula shows us the actual number of each type of atom in a molecule. An example of molecular formula is C2H4. Here we can see that we have two carbon atoms here, and then we have four hydrogen atoms. Now, this shows us the actual number of carbon and hydrogen in this molecule. So the ratio of carbon to hydrogen in this molecule is 2:4. From this ratio, which shows the actual number of atoms in this molecule, we can get the empirical formula to be 1:2. So this is the molecular formula, and then here we have the empirical formula. The same thing happens to the second example here. In the second example here, the actual number of carbon that we have here is 3. whereas the actual number of hydrogen we have here is 6. This is the number of hydrogen and carbon in this molecule. From there, here, we can get the simplest ratio, which corresponds to the empirical formula to be 1:2. And this is the empirical formula. What does this mean? That means that from the empirical formula, you can derive the molecular formula. So there's always a relationship between the empirical formula and the molecular formula. All this were explained in one of my videos in on this channel. So you can do well to go back to the video to watch it and have a better understanding of how to navigate between empirical formula and molecular formula. The third formula that is used to represent organic molecules is the structural formula. The structural formula shows how the atoms are bounded to each carbon atom in the molecule. A very good example of such is this formula that we have here: CH3, CH, CH2. As we can see here, this formula shows the way the atoms are bounded to each other in this molecule. This formula can be compressed to give us the molecular formula, which is C3H6. But molecular formula will not give us much information about the compound because it didn't show us the actual way of arranging the atoms in the molecule. Another example of structural formula is this: CH2, CH2OH. Now, this formula here shows the way the atoms are arranged. This formula is derived from, can be compressed to give us this molecular formula C3H6O. From this molecular formula, we can also get another structural formula, which is this CH3O CH3. Now, these two formulas here shows us the way the atoms are arranged. These two formulas here are gotten from this molecular formula, from this formula that is written up here. Okay. However, we can see that they are not arranged the same way, and that is why structural formula provides more information about a molecule than molecular formula. The fourth formula, which can be used to represent organic molecules, is the displayed formula. A displayed formula will show bonds within a molecule. Emphasis on that, all the bonds within a molecule. For example, let's look at this molecular formula. We have C3H6. Considering this formula that we have here, C3H6, this didn't tell us much information about this compound or this molecule. For us to understand this bit, we can actually show all the bonds in this molecule, and that is written this way. Looking at the formula that we have here, which is the display formula, from here I can see that this molecule, which is C3H6, actually have a double bond, and in between the carbon to the hydrogen atoms, I have just single bonds in between them. And this gives me better understanding of the molecule that I'm considering. It also gives me an idea of the functional group in this molecule. And it also tells me the homologous series to which this compound belong. Another example that we are going to be considering is this molecule.
The molecule that I have on the screen here is the formula is C3H6O. With this formula that I have here, I didn't have much information about it. It didn't display much information. But when I drew this display formula, which is this, the first one we have, the first carbon atom is surrounded with what? With three hydrogen, and each of them have just single bonds. And then the next carbon atom has two hydrogen attached the carbon atom with single bond, and it also attached to an oxygen atom, which is furthermore bounded with what? With an hydrogen atom. Now, this shows all the bonds within this molecule. With this same compound that I have here, with the formula C3H6O, which is the molecular formula, which also represents the empirical formula, I can also get another display formula, which is written down here, and that is the first carbon atom attached to three hydrogen, which is the carbon atom is also in between the two carbon atom. I have an oxygen atom in between them. Now, what does this mean? This is telling me that these two compounds shown here belong to different homologous series, although both of them still have the same molecular formula, which is C3H6O. But with the display formula, I'm able to see all the bonds within the molecule, and that gives me an idea of the functional group that this molecule has. The next formula that is used to represent organic molecule is the skeletal formula. The skeletal formula is a simplified version of the displayed formula. Now, in skeletal formula, you won't show the carbon atom and you won't show the hydrogen atom. Those two atoms are not shown in the skeletal formula. And the reason is because carbon and hydrogen atoms are the bedrock of every organic molecules. In other words, every organic molecules has carbon and hydrogen atom. So hydrogen atoms that are directly attached to carbon atoms are not shown in the skeletal formula. But any hydrogen atom that is attached to another atom, maybe for example oxygen or nitrogen, such hydrogen atoms will be shown. An example of a skeletal formula is this. I'll show how to draw the skeletal formula of this compound here. This compound here, also known as ethanol, has this molecular formula, or have the molecular formula of C3H6O. And this here on the line is the structural formula. The next formula that you see here is the displayed formula in which all the bonds are shown. So right now we're going to be drawing the skeletal formula. Remember that I said that the carbon atom will not be drawn or will not be shown. However, how do we now know the carbon atoms? The edges represent the carbon atom. So I have two carbon atom here, and that means that I'll just be having a stroke. Now, that means that down here, I have the carbon atom, and also here, I also have another carbon atom. That is the meaning. These two carbon atoms here will not be displayed. I just wrote it here so that you have a better understanding of what I'm talking about. So the edges of the line represent the carbon atom. Now, having said that, I also said that the hydrogen that is attached to the carbon atom will not be displayed, will not be shown. And that's why I'm not drawing the hydrogen atoms that are attached to the carbon atoms there. So what are the remaining atoms that I have that I've not shown? and that is the OH bond here. So in order to do that, I'll attach, because the OH bond is attached to the second carbon atom, I'm going to attach that here. So that is the OH bond. Remember that I told you that other hydrogen atoms that are attached to other atoms apart from carbon needs to be displayed. So this is the skeletal formula of ethanol, which has the structural formula of CH3, CH2OH. Another example that we're going to be looking at is a molecule with the molecular formula of C5H12. C5H12. Now the structural formula is written thus: CH3, CH2, 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 CH3. Now it's not every time that you need to draw the display formula before you can get the skeletal formula, because in this case here, I just have carbon and hydrogen atoms only. So what do I need to do? I already know I don't need to show my carbon atoms and the hydrogen that are attached directly to a carbon atom. So all I just have to do here is just to count the number of carbon atoms that I have here. I have 5 carbon atoms. So I start drawing it this way. 1. So here I have 2 carbon atoms already. 1, 2, 3, 4, 5. So I already have 5 carbon atoms that we can count together. So this edge here shows the first carbon atom. I have the second carbon here, the third, the fourth, and the fifth. And so this is my skeletal formula for this compound. Lastly, before we go for today, I need to teach you this formula, and that is the 3D representation. 3D representation is just a version of a skeletal formula, but we do of a displayed formula. It's just another version of a displayed formula. In this case, the bonds are shown like the normal displayed formula. However, you have the bonds, right? You have about 3 different kind of bonds being shown there, or 3 ways of representing the bonds. That is the wedge, the broken line, and the straight line. The wedge bond is said to be sticking out of the paper, while the broken line is said to be sticking into the plane of the paper. Now, a very good illustration for that is looking at the tripod stand. So this will bring us to the end of today's lesson. I hope you have learned more on how to represent organic molecules. We have 4 different methods, 4 different formulas for representing organic molecules. The first one is the empirical formula. The next is the molecular formula. Then we have the structural formula and the displayed formula. Under this displayed formula, we have the skeletal formula, in which you don't show the carbon atoms and the hydrogen that are directly attached to the carbon atom. And then the last one is the 3D representation of organic molecule using the wedges and the broken line and a solid line as well. So please do well to subscribe to my YouTube channel, like, comment, and share this video. See you in the next video. Bye.